Hello everyone, this is Shovik. Welcome to the one-shot video of rearrangement reactions. So we will start with a rearrangement reaction named as a Wagner-Meerwin rearrangement. This is a 1-2 rearrangement reactions of carbocation. So in case of carbocations, it undergoes 1-2 rearrangement reactions. So like if carbocation is this, so there will so if any group is there like any alkyl or any hydride group, it will undergo shifting from here to here, that is 1 2. So that's why it is named as 1-2 rearrangement reactions. So this is the two examples of this rearrangement reaction. First example, this is in this one bicyclic alcohol. It in presence of H plus ion, that is proton, in the acidic medium, it undergoes elimination to form this type of alkene, and in this alcohol, in presence of proton, it gives this type of alkene. So we'll start with the mechanism of the first reaction. So in the first reaction, we have this alcohol, bicyclic alcohol. So alcohol will abstract the proton from the reaction medium, so it will form OH2 plus ion. Next step, there will be removal of H2O, that is water, and it leads to the formation of carbocation. Now you see this carbocation is less stable carbocation, so it undergoes one shifting because this is a 1 to 1 degree carbocation. So it undergoes not 1 degree, this is a 2 degree carbocation. So it undergoes methyl shift from here to here. So it undergoes 1 to methyl shift and it gives 3 degree carbocation, which is a more stable carbocation. Next step, now this plus charge is shifted from this to this carbon, so here to here. Next step, uh, there will be removal of this proton, so it leads to the formation of this alkene. Our next reaction is this is a next example, like this is another type of alcohol. This will abstract the proton from reaction medium and it gives H2O, OH2 plus, and later it leads to removal of this H2O and leads to the formation of this alcohol, like a carbocation, which is a less stable carbocation, this 2 degree. Now it undergoes, if there is no group here to shifting, like this methyl will not shift because this is a bridgehead carbo, then it will form a bridgehead carbocation. If methyl will shift, then it will form a bridgehead carbocation, which is a not stable. So there is nothing to no groups are there to shift. So this carbon will shift from, like it's not stable. So only this carbon will shift from here to here, like this bond will shift. That's why it leads to the formation of this carbocation. Now it is a 3 degree carbocation, which is a more stable carbocation. So it is forming this carbocation. Now we need to rearrange this structure to this. Like how we will rearrange? Like we need to give run numbering. Like it will start from 1 2, like it will start from like this: 1 2 3 4 5 and 6. This will be 7. So 7. Now this 7 carbon will be bridgehead carbon. So this is 7. Now it will stand. Now here this numbering will start from, this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. Next step, it leads to the removal of this proton, and it leads to the formation of this alkene. There will be another example, like another alcohol. It will abstract the proton from acidic medium, and it leads to the formation of H2O, and there will be removal of this H2O, that is water, and it leads to the formation of the 2-degree carbocation, and there will be 1,2 hydrogen shift. First, like if there is any hydrogen is there, then it will shift faster than any alkyl group. So here first hydride will shift, so it undergoes shifting from this hydride will shift from this carbon to this carbon, and it leads to the formation of this 3-degree carbocation. Next step, like there will be one proton is there, so it undergoes removal of this proton, and there will be uh, mm, formation of this alkene. This is another type of Wagner-Merwin rearrangement. This is another type of Wagner-Merwin rearrangement reaction. So this is a memory effect of on solvolysis. So we are doing solvolysis of this halide. So this is 2 isomer. This is both compounds are same, but isomers are different. Here this is endoisomer because this halide is towards the double bond. That's why it is endoisomer, and this halide is away from the alkene. That's why it is exoisomer. Now in presence of H2O, like proton, like water, it gives this product as a major, and in presence of this is a allylic alcohol. This is a allylic alcohol, and in presence of H2 exoisomer gives tricyclic compound. But compounds are same, only isomer is different. So we will see the mechanism. Here you see, like it will, when this is a endoisomer. So in first step, there will be removal of this X like halide ion or X minus, and it leads to the formation of a carbocation, and this bond will shift from here to here. So it leads to the formation of this carbocation. And same in case of exoisomer, there will be this bond will shift, and it leads to the removal of this halide ion. So it leads to the formation of same carbocation. Yes, each same, both carbocations are same, but at the end it leads to the different product as a major. That's why it is known as memory effect. So now we will see here, like here this bond will break, and it will form, this bond will break, and it will shift it to here, and it leads to the formation of this carbocation. Later we have H2O like water in our in our reaction medium, so it will attack on this one, and it leads to the formation of the alcohol, which is a allylic alcohol. Now we will do numbering of this. Now we need to convert this structure to this structure. So we will do numbering again. 1, 2, 3, 4, 5, 6, 7, 8. So this will be 8, and we started from this 1, 2, 3, 4, 5, 6, 7. Okay, so it converted to a allylic alcohol. Now in case of exoisomer, this double bond will be migrated, and it will shifted to here, and it makes bond with this, so it leads to the formation of the carbocation. Next step, like this H2O will attack on this carbocation, and it leads to the formation of the tricyclic compound. This is a tricyclic compound, tricyclic alcohol, because three cyclic compounds are there. This is one cyclic, this is another, which is bicyclic, another cyclic, that is another bond is formed, that's why it is another cyclic. So total is tricyclic. Our next rearrangement reaction is pinacol-pinacolone rearrangement. This is a acid catalyzed rearrangement reaction of 1,2-diol. 1,2-diol means this is hydroxyl, hydroxyl. So 1, 2. That's why 1,2-diol. So in this case, this is a first example of the pinacol-pinacolone rearrangement in presence of acid. So it gives ketone, and this in 1,2 alcohol it gives this ketone, and followed by this we have these 4 examples. Now we will see the mechanism of these 4 examples. So we will start with the first example. So first example, so we have proton in the reaction medium. So here you see hydroxyl group have lone pair on its orbital, like oxygen have lone pair on its orbital. So it will abstract this proton, and it leads to the formation of OH2 plus. Later there will be removal of this H2O, and it leads to the formation of this carbocation. And now there will be there will be 1,2 shift of methyl, and it leads to the formation of this carbocation. This one, like this carbocation is much more stable than this carbocation, because both are 3-degree carbocation. But in this case, in case and there will be lone pair contribution. This carbocation will be more stable by this lone pair of this oxygen. That's why it is more stable carbocation. So that's why this shifting is possible. So in the later step, this proton will remove, and it leads to the formation of this ketone. Okay, this is the second example. Like now this proton, like this hydroxyl group, will abstract the proton from the reaction medium. It leads to the formation of OH2 plus, and there will be removal of this H2O, and it leads to the formation of this carbocation. Now you can think like this hydroxyl also can this kind. There is a possibility like this hydroxyl will abstract the proton, like this hydroxyl group will abstract the proton, and it leads to the formation of this carbocation, and later it leads to the formation of this carbocation. But this carbocation is much lesser stable than this carbocation. This is less stable, that's why it is not possible. It is not possible because in this one this carbocation like it is conjugated to the 2 phenyl rings, so it will be so this carbocation will be stabilized by the two aromatic system. But in this case it will be stabilized by only 2 methyl groups. So that's why this stable carbocation will be formed, which will be more stable. Now here you see like there will be 1 2 shift of this methyl group, and it leads to the formation of this carbocation, and later there will be removal of this proton, and it leads to the formation of this ketone. This is the third example. Now we have a cyclic group. This is a cyclic group, cyclopentane, with a cyclic system. So in presence of H plus, it will abstract the proton, and it leads to the formation of H2O. Now there will possibility like this will abstract, both can abstract. There is a possibility, but so it leads to the formation of both like both carbocation. This carbocation, like if H2 will remove and this H2 will remove, so it leads to the remove. Uh, so possible carbocations will be these two. But here you see this carbocation is much more stable, because this is like it will be stabilized by two phenyl systems, but in this case this carbocation is less stable, because it is stabilized only by these two methyl, like two alkylic groups. This is, you can say, like two alkylic groups. So this carbocation is much more stable than this carbocation. So in the next step it undergoes ring expansion. Like this bond will break, and it will shift it to here. So 1 2 shift, it undergoes 1 2 shift, and it leads to the formation of this carbocation. Next step, there will be removal of this H plus, and it leads to the formation of this ketone. This is our next example, like two cyclopentane, and this is 2 cyclopentane, and we have 2 alcohol, like this is 1 2 diol with 2 cyclopentane. Now this hydroxyl group will abstract the proton, and it leads to the formation of this H2O plus. There will be removal of this H2O, and it leads to the formation of this carbocation. Now there will be shifting. This is 3 degree and 3 degree carbocation, and this bond will shift, and there will be shift from here to here. So there will be shift ring expansion, like from 5 degree to from 5 member to 6 member. And here you see this, and this carbocation is much more stable. That's why this ring expansion is possible here. Now here you see like this carbocation is stabilized like extra by hydroxyl group. Can also stabilize by hydroxyl group by electron donation, lone pair donation. Okay, so next step, there will be removal of the proton, and it leads to the formation of this ketone, and this is one type of spiro compound. Our next reaction is semi-pinnacle rearrangement. This is a 1 2 shift of the hydrogen or alkyl group, which leads to the formation of aldehyde or ketone in case of alpha beta epoxy alcohol. That is alpha beta epoxy alcohol. This is alpha beta epoxy alcohol. That is alpha. This is alpha, and this is beta epoxy alcohol. Okay, and allylic alcohol, this is allylic alcohol, which, and this is allylic alcohol, and and there will be heteroatom present in the second position, like 2 position. If we say this one, then it will be 2, so 2 heteroatom. So in case of pinnacle rearrangement, we are seeing like there will be 2 hydroxyl group. In this case, this hydroxyl group is replaced by this epoxy group, allyl group, and this heteroatom, that is like some heteroatoms like halide, some living groups like tosyl, and triplets, it's OTF, OTS, OMS, these leaving groups. Okay, and it leads to the formation of different carbonyl compound. So we will see the first mechanism of fast reaction. Like this is a acid catalyzed reaction. So this is a epoxy alcohol, alpha beta epoxy alcohol. So first step, it will abstract this uh, epoxide have lone pair, so it will abstract this BF3 because it have tendency to open up this ring. So that's why this lone pair will abstract this BF3. Okay, so it leads to the formation of this zwitter ionic species. Later, like this bond will shift, like this bond will break and it will shift here. That is one to shift, which is known as one to shift, and it leads to the removal of breaking of this bond, and it leads to the formation of this carbocation. And next step, there will be removal of this proton and this removal of this uh, BF3. So it leads to the formation of O minus and this carbocation. This O minus will abstract the proton, this proton, and it leads to the formation of ketone and here alcohol. So it leads to the formation of here ketone, here alcohol. Next example is like this is in case of allylic alcohol. This is allylic alcohol. So in presence of acid, this double bond will abstract the proton and it leads to the formation of carbocation. This is a 2-degree carbocation. If we do so that's why it is undergoing 1 to shift, that is this phenyl will shift from here to here, so it leads to the formation of this 3-degree carbocation. And next step, like here there will be removal of this proton and it leads to the formation of this ketone. Next, like this is another example, like in case of 2 heteroatom. So in this reaction will be done in presence of base. So base will abstract the proton. This base will abstract the proton and it leads to the formation of this oxide ion. And now this oxide ion will like O minus will undergo this will undergo one ring. There will be 1 to shift, like this bond will shift from here to here and it leads to the removal of this this halide or heteroatom. So it leads to the formation of cyclopentane, which is a ring contracted product. So it undergoes ring contraction. This is CHO and here R. So this is aldehyde. So it forms aldehyde here. Next rearrangement reaction is Payne rearrangement reaction. So this is a base catalyzed conversion of 2,3 epoxides, like 2,3 epoxy propanol. Like if we do numbering from, this is a starting material, this is 2,3 epoxy alcohol. We'll do numbering from here 1, 2, 3. That's why this is 2,3 epoxy alcohol to the 1,2 epoxy 2 1 2, this is 1 2, epoxy 3 all, this is 3 all, propane 3 all. So in presence of base. So now we will see the mechanism of this reaction. So we are using tar-butyl thiol. So in presence of this base, it undergoes removal of this proton and it leads to the formation of this anion. This anion will abstract the proton, like it have one proton. This this epoxy alcohol have one proton, so it will abstract this proton and it leads to the formation of this uh, anion, like oxide ion. Now this undergoes NGP type of rearrangement, like this anion will undergoes attack to the uh, epoxy alcohol from the opposite side. That is, here epoxide is on the is present on the below the plane, so there will be attack will be from the attack will be from this above the plane. So there will be a SN2 attack and this bond will break and it leads to the formation of this, and this epoxide, it form once again epoxide, and here O minus, it will abstract the proton from tar-butyl thiol and it leads to the formation of this 1,2 epoxy alcohol, like 3 all, 1,2 epoxy 3 all. Our next rearrangement reaction is Jaborsky rearrangement reaction. This is a base catalyzed rearrangement reaction of alpha haloketone. This is alpha haloketone. This ketone. So here alpha, in the alpha position, ketone, like some halo group will be present. So in presence of sodium methoxide as a base, it will undergoes a ring contraction, like 1,2 shifting. It undergoes 1,2 shifting and it leads to the formation of ester. This is also same. This is another example and this is another example. Now we will see the mechanism of the reaction, these three reactions. First reaction, like for the mechanism of the first reaction is this is our alpha halo ketone. We have sodium methoxide. We are using sodium methoxide as a base, so it will abstract the proton from here and it leads to the formation of this anion. Now this anion will attack on the on this carbon and it leads to the removal of this bromide ion, that is halo group, and it leads to the formation of this three-membered ring. Okay, this three-membered ring is very unstable species, so in presence of another source methoxide ion, like now methoxide ion will acting as a nucleophile, not a base. So it will attack on the carbonyl center, so it leads to the opening of this three-member species and this bond will break and it leads to the formation of this cyclopentyl group, which with methyl ester and anion. Now this anion will abstract the proton from methanol and it leads to the formation of this cyclopentyl ester. Okay. Next example is we have sodium methoxide. Now this sodium methoxide will abstract the proton of this alpha halo ester, this proton only, and it leads to the formation of this anion. Because if it will abstract this proton, so it will if it will abstract this proton, so here minus ion will form. So here if now there this anion will not that much stable like this anion, because this anion is stabilized by both this aromatic species and ketone species, ketone, this carbonyl group. But in this case this carbon this like this anion is only stabilized by this like ketone, so it is a not stable species. So that's why this methoxide will undergoes attack on this this hydrogen, and it leads to the removal of this proton, and it leads to the formation of this anion. Next step, this anion will attack on the attack on this carbon, and it leads to the removal of this chloride. So it leads to the formation of again this cyclopentanone type of species. So this species is not that much stable enough, so it undergoes attack by this methoxide ion. So this there will now this methoxide ion will attack on the carbonyl species. Now there is a two possible, like this bond will break this side or this side, but like it will break this side and this side. But if it will break this side, it will form anion this side. This anion will not be stabilized by this this mm, aromatic species. That's why this anion is this bond is breaking this side only. So anion will form here. So this anion will abstract the proton, and it leads to the removal of this methoxide, and it leads to the formation of this ketone, like no ester. Our next reaction is quasi-Favorsky rearrangement reaction. In case of Favorsky rearrangement reaction, we have seen like this is a alpha halo. This is a alpha halo carbonyl group. So we have one methyl like alpha hydrogen here. In case of carbon, into the there will be one alpha hydrogen to the carbonyl group. So this alpha hydrogen will be abstracted by base. So it's, after that this reaction, this and that rearrangement will happening. But in case of quasi-Favorsky rearrangement, there will be no alpha hydrogen. You see this compound, like this is a alpha halo carbonyl group. Here no like there will be no alpha hydrogen is there. This is a alkyl group, so it undergoes 1-2 shifts of this alkyl group from here to here, and it leads to the removal of this halide ion. So how it will happen, now we'll see. So we have nucleophile. So this nucleophile will attack on the carbonyl species, and it leads to the formation of this tetrahedral intermediate. Later this O- will come back, and this alkyl group will shift from this carbon to this carbon, and there will be removal of this halide group. So it leads to the formation of this carbonyl species. Next example, this is also another next example is like here you see this bromide, and this bromide and this tert butyl species, this bromine and this tert butyl group is in the same plane. So it will be in this tert butyl group in the above the plane, and this bromide group is above the plane, and this COPH group is above the plane, because we are converting this cyclohexane derivative to the chair conformation. Now this we are reacting this species with a nucleophile known as hydroxyl. This hydroxyl will attack on the carbonyl, and it leads to the formation of this tetrahedral intermediate. This so after this minus will come again, like will shift from here to oxygen to this carbon, and there will be a breaking of this phenyl, and this phenyl will shift from this carbon to this carbon, that is 1 to shift, and this bromide will shift from this bromide will eliminate, so it undergoes a 1 to shift, so it leads to the formation of these products. So it leads to the form. So we'll convert this CR conformation to the actual structure. So tar butyl group will be present same as it. You see this phenyl group are present above the plane. So this phenyl group will be above the plane, and CO2 which will be present below the plane. Next example, like this is another example. This is two fused rings, and in the junction of the two fused rings, a ketone is there. So in presence of this sodium hydroxide, this hydroxide will attack on the carbonyl, and this it forms this tetrahedral intermediate, and this O minus will come again, and this bond, like this bond will shift from here to here, and it leads to the removal of this bromide, that is which is known as 1 to shift. So it leads to the formation of this 2 cyclopentyl, because if it will if this bond will shift, then this bond will shift from here to here, so it leads to the formation of a bond like this. Okay, so now we'll count the number of carbons present in both sides. Here you see, like 1 2 3 4 5, so 5 membered ring. This side 1 2 3 4 5, so 5 membered ring. So that's why two 5 membered rings are present, like are joined to each other. Here CO2 is, that is like it forms a acid, carboxylic acid. Our next reaction is Beckmann rearrangement reaction. This is a rearrangement of oxime in presence of a Lewis acid or solid catalyst like aluminum trioxide, etc., and it leads to the formation of amide. So first we will see the reaction. First we will see first example. This is the first example. So oxime will be formed from the ketone. This is ketone. Ketone reacts with hydroxylamine to give oxime. Now this oxime will react in presence of acid catalyst. So this lone pair of this oxime will undergo attack on this H plus, and it gives a OH2 plus, this cation, and then this lone pair will come here, will shift here, and this the alkyl group which is anti to this OH, so that one will only shift to the nitrogen, and this H2O, and it leads to the removal of this H2O. So it is known as 1 to shift. So it gives this nitrilium ion. This is nitrilium ion, and later if we add in presence of H2O, this H2O will attack on the carbon, this bond will break, and it gives this it gives this enol, like enol type of derivative. After this it undergoes tautomerization to give this amide. Now we will see the migratory aptitude of different groups. This is the migratory aptitude of different groups, like migratory aptitude means between this R and R dash, which one will shift faster to the nitrogen. So if hydrogen is there, then hydrogen will have the greatest migratory aptitude. So first will be hydrogen, then phenyl, then 3D, and then tertiary, then 2-degree, then primary, then methyl. Now we'll see the next example. This is the ketone. So this ketone reacts with hydroxylamine. It gives oxime. Now in presence of this Lewis acid catalyst, that is aluminum chloride, it will attack on the aluminum chloride and it leads to the removal of the chloride. So it will form this oxygen or aluminum bond. Next step, like now, which here you see this is 2-degree carbon and this is 1-degree carbon. No, this is 2-degree and this is 3-degree. Okay, this is 3-degree carbon. So 3-degree carbon have greater migratory aptitude than 2-degree carbon. So 3-degree carbon will undergo shifting into the nitrogen and this bond will break. So it leads to the formation of this 7-membered ring, because it undergoes ring expansion when this bond is shifted to carbon, when this carbon is shifted from this carbon to nitrogen. Next step, it undergoes reaction with H2O. This H2O will attack on the on this carbocation. So it will form this amide. Next reaction is like this is oxime. So in presence of pyridine, it will abstract the proton, so it will form O minus. So it will form O minus, and in presence of this tosyl chloride, it will attack, this O minus will attack on the tosyl and it leads to the removal of this chloride ion. So it forms this O tosyl, which is a beta leaving group. This is a beta leaving group. So in presence of aluminum chloride, it undergoes this bond will shift, because this is a 3-degree carbon, and here you can see 3-degree, or this is phenyl attached carbon. So and this is 1-degree carbon. So this bond will be shifted much more faster than this bond. So this bond will shift and it leads to the removal of this OTS. So this bond will shift, so it leads to the formation of this ring extended carbocation. This now in presence of H2O, this leads to the formation of this amide. This is our next example. Now if there is any bromide, so they are like here you see like which this bond is anti to this OTS. Okay, so then only this shifting is happening. Mostly the bond which is anti to this OH or OTS, this leaving group, that one only shifting. Syn groups are not shifting. This carbon will not shift to this nitrogen. This carbon only shift to the nitrogen. But in case of bromide, it will be changed. But now we will see like in presence of pyridine and tosyl chloride, it gives OTS, which is a leaving group. Now it we know bromine have lone pair of electrons, so it undergoes NGP. Okay, so lone pair will attack on the nitrogen and it leads to the removal of this tosyl, like OTS group. So it will form this intermediate, 5-membered intermediate. Next step, like now it undergoes like this bond will not shift here. It can't shift here, because if it will shift here, then this bond will not break. So here this bond will only break. So this bond will also break, because if this bond will break, this bond will not break. So if now in this case you see like the bond, this bond is seen to the this OTS. This bond is seen to the OTS. So this bond is shifting, not this bond. So it undergoes like shin want to shift here in this case. So after this it forms this cyclo like say 7-membered ring, and after this it will reacted with this H2O and it will give this amide. Now we will see this another example. As you see this OH, this is oxime. So oxime like OH will attack on this PCl5, which is a type of solid catalyst. So it will so by reaction on this PCl5 it leads to the removal of this Cl, and overall there will be removal of HCl. So it will form this oxygen and phosphorus bond. Next, like this, there will be possibility like this one, this bond like this carbon, or this carbon will like this carbon, or this carbon will shift to the nitrogen. But in this case you see like this is a 2-degree carbon and this is a 1-degree carbon. So this 2-degree carbon will migrate faster than this 1-degree carbon. So this 2-degree carbon will migrate to this nitrogen. Okay, and it leads to the removal of this bond. Next step, it leads to the formation of this intermediate. Here you see like after rearrangement, this like there will be no change in the configuration. This ethyl group is present above the plane, but in this after rearrangement it is present as such like above the plane. So there will be retention of configuration happens. So after this, if it will react with H2O, it will give amide again. Next is Beckmann fragmentation. This is a breaking of CC bond, which is alpha to the nitrilium ion, and it leads to the formation of carbocation and nitrile. So if in this case you see like this bond will break, that is CC bond, which is CC bond to the carbon, CC bond which is alpha to the nitrilium ion. This bond will break and it leads to the formation of this carbocation and nitrile. And this carbocation this bond is breaking. There is a reason like it forms the stable carbocation, then only this bond is breaking, because it forms 3-degree carbocation, which is a more stable carbocation. Now after this there will be removal of H plus from here, and it leads to the formation of this 5-membered ring. Here you see like H plus is above the plane and CH to Cn is below the plane. So here hydrogen is above the plane and CH to Cn is below the plane. And the next reaction, like next example, is in presence of sulfonyl chloride, this oxime will attack on the sulfonyl chloride and it leads to the removal of HCl, like total HCl. So it leads to the formation of O and sulfur bond. Next step, again like this bond will break, which is CC bond, which is alpha position to this nitrilium ion, and this bond will break and it leads to the formation of this stable nitrile and this this carbocation, and this carbocation is stabilized by this lone pair of this oxygen. That's why this carbocation is formed here. So after this bond will break in presence of H2O. This bond will break and it leads to the formation of here aldehyde and here alcohol. Our next reaction is Baeyer-Villiger oxidation. This is an oxidation of a ketone. This is a ketone to an ester. This is a ester, which is a cyclic ester, by using peroxo acid. This is a peroxo acid. Peroxo acid means there will be the peroxo bond in the compound. Not this. 1, 2, 3, 4, 5. Okay, this is a peroxo acid. This is, here you see here is a peroxo bond is there. That's why it is peroxo acid. Now, in presence of peroxo acid, so how it will react? The peroxo acid, this oxygen have lone pair, so lone pair will attack on the ketone and it leads to the this bond will shift. If I okay, here this is peroxo acid. Okay, so it will react, this lone pair of oxygen will react on this carbonyl and this bond will shift and it leads to the formation of this intermediate. Next step, this again there will be shifting like Beckmann rearrangement type of reaction, like this bond will break and there will possibility like this one or this carbon, or this bond or this bond will shift to this oxygen. Here you see this carbon is 1 degree and this carbon is 2 degrees. So 2 degree will have much more migratory aptitude than 1 degree. So 2 degree carbon will shift to this oxygen. So this bond will shift to the oxygen and this bond will break. So it leads to the formation of CSIR 7-membered ring. Okay. Here you see the migratory aptitude. First it will be 3 degree, that is tertiary, then 2 degree, then phenyl, then 1 degree, then methyl, then at the end it will be hydrogen. Our next reaction is this is our next example. In presence of MCPBA, now we are doing reaction in presence of MCPBA, that is metachloroperbenzoic acid. This is metachloroperbenzoic acid. Okay, and so oxygen have lone pair, it will attack on the ketone and this bond will break and it leads to the formation of this intermediate. Now there is a possibility, that is this bond will shift or this bond will shift. Now you see this is 1 degree carbocation, this is 2 degree carbocation. Okay, so in this case this one will shift instead of this, so this bond will shift to the oxygen and it leads to the removal of this this bond. So it leads to the formation of this this rearranged product. Okay, because now there will be another exception is there, like same example, OBN. Here if any tert butyl, any bulky group is there, then MCPBA, if we add MCPBA, so it will give this intermediate OH OCO, this aryl group. Okay, here Now because this here there is an exception, like this is a 3 degree carbon 3 degree this is a 3 degree carbon, this is a 3 degree carbon, but here we can presence of this bulky tertiary bulky group. This is a very bulky group, so presence of this group, there will be shifting, this bond will shift, like this CH2 will shift, not this one, this bond will not shift. So this bond will shift to the oxygen, and it will give this here CH2, here O, Bn, this one, and here tertiary butyl group. So this is an exception. Now our next reaction is Wolff rearrangement. This is a thermal or photochemical decomposition of alpha diazo ketone, alpha diazo ketone 2. This is alpha diazo ketone, this is ketone, and this is diazo to ketene, this is ketene. And further it will react with carbonyl derivatives, or further it will react to give carbonyl derivatives like any ester, acid, amide, etc. So first example you see, in presence of acyl chloride, first we will take acyl chloride. So acyl chloride will react with diazomethane to give this alpha diazo ketone. This is alpha diazo ketone. Now this alpha diazo ketone undergoes isomerization to give this intermediate. Next step, this minus will come here, not this one, like this bond will shift, like this bond will break, so it leads to the removal of the nitrogen in presence of thermal condition. So it leads to the formation of this carbene, but this carbene is very unstable intermediate, so it will be rearranged, like this lone pair will shift here, and this alkyl group will shift here to form, and it will rearrange to form this ketene. This is ketene. Now in presence of any nucleophiles, like here we are using alcohol, so in presence of alcohol it will react with this alcohol lone pair will react on the carbonyl carbon of the ketene, and this bond will break, and it leads to the formation of this ester. Now next example you see, like here this is also another type of alpha diazo ketone. So in presence of thermal condition, it will undergo removal of nitrogen, so it will give this carbene. Now this carbene undergoes rearrangement to the ketene, so this lone pair will shifted to here, and this bond will shifted this to this carbon, so it will form this ketene. In presence of any methanol we are using, if we are using methanol, so methanol oxygen will attack on the on the carbonyl carbon, and this bond will break, and it leads to the formation of an ester. Next, this is diketo, like diketo diketone. This is diazo. This is alpha diazo diketone. So under the thermal condition, it will undergoes the removal of the nitrogen, so it leads to the formation of this carbene. So after this, this carbene will rearrange, like this lone pair will this electron pair will shift to this bond, and this bond will shift to this bond will shift, this lone pair will shift, and this bond will shift like this. Okay, and it leads to the formation of this 5-membered intermediate and ketene. This is a ketene. Now, in presence of methanol, it will react with this ketene, and it leads to the formation of this ester. Our next example is Porteous rearrangement. This is a rearrangement of an acyl azide to an this is acyl azide to an isocyanate. This is isocyanate. So under the thermal decomposition, so we'll start with acyl chloride. This is acyl chloride. This acyl chloride undergoes reaction with sodium azide. Sodium azide is present as azide ion. Azide ion will attack on the carbonyl carbon, and there will be removal of this chloride, and it leads to the formation of this acyl azide. And acyl azide is present in this form. Now we'll now it will be like we will isomerize. We will do isomerization of this azide. So this anion will shift here, and this bond will shift on the nitrogen, and it will form anion here and nitrogen plus. Next step, this undergoes rearrangement, and under the thermal condition there will be removal of this nitrogen, and this minus will shifted to this carbon, and this alkyl will shift to this nitrogen, and it leads to the removal of this nitrogen. So it leads to the formation of this isocyanate. And under the like if it will react with any H2O like water, so it will react like H2O will attack on the carbonyl carbon, and it leads to the formation of this amide like carbamide. This is a carbamide. So under the thermal condition it will undergoes removal of the H2O like CO2, not H2O, CO2, and it will form this amine. If it will react, now this nucleophile, if any other nucleophile will attack, so nucleophile will attack like it will attack on the carbon, and this bond will break, and it leads to the formation of this amide. We have another example like this is a carboxylic acid. So in presence of this sodium tarbute oxide, this is a base, so this will abstract the proton of this carboxylic acid, and it will form this anion of this carboxylic acid. It will form like this. Okay, so this anion will attack on this carbonyl carbon of this reagent, and it leads to the removal of chloride ion, and it leads to the formation of this as anhydride. Now this chloride will again attack on the carbonyl, and it leads to the removal of this carboxylate ion, and it leads to the formation of this chloride, acyl chloride. And in presence of sodium azide, it leads to the formation of like acyl azide. Now in presence of this heating condition, it undergoes removal of nitrogen, and it leads to the formation of isocyanate. Now in presence of this alcohol, it will attack on the carbon, and this bond will shift, and it leads to the formation of this ester. This is ester, and this is amide. Like you can say this is an amide type of derivative. Our next reaction is Lewisian rearrangement. This is a transformation of an hydroxamic acid derivatives to an isocyanate by activating the hydroxamic acid. Like this is a hydroxamic acid. We are activating this hydroxamic acid by O acylation, O arylation, and O sulfonation. Here we are using the base, so base will abstract this proton of this hydroxamic acid, and it leads to the formation of O minus. Okay, now O minus will react with R2X here, and it leads to the removal of this X minus. Okay, here X will be halide, any halide or any living group. Okay, and it leads to the formation of activated form of the activated form of this hydroxamic acid. Here R2 will be acyl, like MECO. This is acyl. Aryl, like any aryl derivative, or R2 will be any sulfonyl derivative like SO2 R dash. This is this type of derivatives. So now if you are using another equivalence of base, so base will abstract this proton, nitrogen and hydrogen proton, like it abstracts this NH proton, and it leads to the formation of this carbon anion. Next, like this anion will shift to this bond, and this alkyl carbon will shift to this nitrogen, and there will be removal of the R2O minus, and it leads to the formation of the isocyanate. In presence of methanol, like methanol will attack on the carbon, and this bond will break, and it leads to the formation of an amide.